previous sections, we've provided the foundational skills for constructing and analyzing logical arguments. All logical arguments include a set of premises that support a claim or conclusion, but not all logical arguments are valid and sound. A logical argument is valid if its conclusion follows the premises, and it is sound if it is valid, and all of its premises are true. A false or deceptive argument is called a fallacy. Many types of fallacies are so common that they have been named. So we're going to focus on two main forms of logical arguments, or two main forms logical arguments can take. While inductive arguments attempt to draw a more general conclusion from a pattern of specific premises, deductive arguments attempt to draw specific conclusions from at least one or more general premises. Deductive arguments can be proven to be valid using Venn diagrams or truth tables. Inductive arguments generally cannot be proven to be true. They are judged as being strong or weak, but like any opinion, whether you believe an argument is strong or weak often depends on your knowledge of the topic being discussed, along with the evidence being provided in the premises. Hasty generalization is the name given to any fallacy that presents a weak inductive argument. Be careful. Premises may be true or false. If a premise is false, the claims made by the argument should be questioned. So we start with the law of detachment. The valid form of a conditional argument that asserts that if both the conditional, if P then Q, and the hypothesis P are true, then the conclusion Q must be true. The law of detachment is also called affirming the hypothesis or antecedents. Symbolically, it has the form if P then Q and P then Q. And we look at it like this. Our first premise is if P then Q. Our second premise is P, and our conclusion is therefore Q. That's what this symbol means, therefore. So if we recall from the truth table for a conditional statement, the only time the conditional is true is when the hypothesis P is true, or is also true. The only place this happens is in the first row where Q is also true, confirming that the law of detachment is valid. Another way to verify that the law of detachment is a valid argument is to construct a truth table for the argument if P then Q and P then Q, and verify it is a tautology. So we have our P's, we have our Q's. We have our if P then Q statement, which is only false when P is true and Q is false. Then we have our if P then Q and P statement, which is only true when if P then Q is true and P is true, which is the top one. Then we have if P then Q and P then Q. So I'm looking at this column here and this column here, and I'm looking at a conditional. And the only time a conditional is false is when the first part is true, second part is false. And we have true, true, or true, true, so true. We have false, false, true. We have false, 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 true, false, false. So they're all true. So we have a tautology, so it is valid. So remember that an argument can be valid without being true. For the argument to be proven true, it must be both valid and sound. An argument is sound if all its premises are true. Each pair of statements represents the premises in a logical argument. Based on these premises, apply the law of detachment to determine valid conclusion. So, if my classmate likes history, then some people like history. My classmate likes history. Therefore, some people like history. Looking at it, history. We have if P, then Q. Well, let's do this here. If P, then Q, P, therefore Q. This is what we're looking for. If you do not like to read P, and some people do not like reading Q, you do not like to read P. So again, we're looking at if P, then Q, P, or yes, P, therefore Q. So therefore, yeah, therefore, some people do not like reading. Remember, the quantifier some means at least one. Another form of a valid conditional argument is called the law of denying the consequent. Recall that the conditional statement if P then Q is logically equivalent to the contrapositive if not Q then not P. So if the conditional statement is true, then a contrapositive statement is also true. By the law of detachment, if not Q is also true, then it follows that not P must also be true. So here's what we're looking at. The premise is if P then Q and not Q, therefore not P. We can describe this as if antecedent then consequent. So where the law denying the consequent gets its name. So let's verify the law of denying the consequent is a valid argument by constructing the truth table. So we're looking at P and Q again. So true, true, false, false for Q. True, false, true, false. Here we're doing not P, so false, false, true, true. Q is false, true, false, true. Now we're looking at if P, then Q. This is the only line that's false. If we have P true and Q false. I'm looking at false here and true everywhere else. Now I'm looking at if P then Q and not Q. So I'm looking here, and I have an and statement. And the only time an and statement is true is when both are true, which is here. False, false, false. And now I'm looking at, and again, typo, and then not P. So when is an if-then statement false? The only time it's false is when I have a true and a false. So I'm looking here, and then I'm looking here. So the only time I have to be concerned is when it's true in the first statement, the antecedent, and false in the consequent. But the only time it's true in the antecedent is here, and it's also true in my consequence, not P. So that's true, and everything else is true too. So I have a tautology. Tautology meaning every truth value is true, which makes this valid, which fits with what we've proves that it's a valid statement. So each pair of statements represents the premise in a logical argument. Based on these premises, apply the law of denying a consequent to determine a valid conclusion. So if my classmate likes history, and some people like history. So this is P, and this is Q, and this is not Q. So my result is therefore not P, which would be my classmate does not like history. All right, let's look at another one here. If Homer does not like to read, then some people do not like reading. All people like reading. P, Q. Now remember the negation of some is all. So this again is a negation of not P, Q. Negation of Q. So therefore I'm looking for the negation of P, which would then be Homer likes to read. One more here. If the polygon has 5 sides, label that P, then it is not an octagon. We'll call that Q. The polygon is an octagon. That's the negation of Q. So again, I'm saying therefore the negation of P. The polygon does not have 5 sides. So next we look at the chain rule for conditional arguments, another form of valid conditional arguments, also called a hypothetical syllogism or the transitivity of implication. Recall that the conditional statement, if P then Q, can also be read as P implies Q. This is where the name transitivity of implication comes from. If you remember, the transitive property for numbers states that if 3 is less than 4 and 4 is less than 5, then it follows that 3 is less than 5. The chain rule extends this property to conditional statements. If premises of the argument consist of 2 conditional statements with the form if P then Q and if Q then R, then it follows that if P then R. And here is our symbolic form. And here is our argumentative form. And let's verify the chain rule by constructing a truth table. So this one gets a little tougher. Let's see. We have true, 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 false, 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 false. Then I have true, true, false, false, true, true, false, false. And this is how you should do it anytime you have 3 statements. It just keeps it orderly. And then true, false, true, false, true, false, true, false. So now first I'm looking at if P then Q. And that is only false when P is Q and T is false, or Q is false. So that's here and here. Otherwise, it's true everywhere else. True, true. That's false. If Q, then R. So I'm looking at Q and R. And when is Q true and R false? That's here. So it's false here and here. And everywhere else it's true. Now we're going to combine those with an and as an and statement. And when is an and statement true? An and statement is true when both are true. So true, true, true. True, false, 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 true, false, false, true, false, true, 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 false, false, and these two are both true, true. So now I'm looking at if P then R. So we're looking at true, false, true, false. So that's false. And true, false. So that's false. Everywhere else is true. And now I'm looking at the conditional. If this column, then this column. And really all I have to do is look at where is it true here. And then see if it's false here. Otherwise it's true. I have true and true, so I'm good. It's false here, so that's going to be true as well. Here and here as well. Here I have true and true, so it's true. Here I have false, so it's going to be true. Here I have true and true and true and true. And again, we have our tautology, so we have a valid statement. This shows that this works. Now let's look at some words. I think this is the last example. Each pair of statements represents true premises and a logical argument. Based on these premises, apply the chain rule or conditional arguments to determine a valid and sound conclusion. So I have if my roommate does not go to work, that's P, then my roommate will not get paid, that's Q. So I have P's and Q. If my roommate does not get paid, that's Q. Then my roommate will not be able to pay their bills, that's R. So then I have Q, if Q, then R. So therefore, if P, then R. I'm looking at P, if my roommate does not go to work, then this is R now. They will not be able to pay their bills. Okay, so let's look at the next one here. If penguins cannot fly, we'll label that as P. Then some birds cannot fly, we'll label that as Q. If some birds cannot fly, again, this is Q, then we will watch the news, and this is R. So again, I'm looking at if P, then Q, if Q, then R. So I'm looking for P, then R. So we have P if penguins cannot fly. Now I'm looking at R. Then we watch the news. I'm not sure what penguins flying has to do with watching the news, but okay. Last one. If Marcy goes to the movies, then Marcy will buy popcorn. Q. If Marcy buys popcorn, Q, then she will buy water. R. So again, I'm looking at P. If Marcy goes to the movies, then R. Then she will buy water. And that finishes up this last section.